Well, first I'd like to start with thanking the organizers of the meeting for the invitation to come to Dublin and finally get to the source of Guinness. I'm also happy to be here and not flying home today since the government decided to stay open for 2 more months at least. But now I just have to look forward to Hurricane Joaquin, which may hit North Carolina this weekend. So.
Yeah.
I'm going to tell you about ToxCast. It's always hard choosing what to focus on, so I tried to keep it pertinent to what we were discussing here, but it may wander a bit. I don't really need to introduce why we're doing this ToxCast predictive toxicology project, but I did want to emphasize that the unique or the specific reasons for the EPA to pursue this is because we have large lists of chemicals with very little toxicity data, and we were trying to develop methods of data generation and use that data to build predictive models and also understand mode of action and mechanism of action. The overall strategy of ToxCast is similar to the Tox21 program to identify targets or pathways that are linked to toxicity, which is now known as the AOP method, to identify or develop high-throughput assays for those targets or pathways, and then to use the in vitro and in silico data from those assays and in silico methods to predict the in vivo, primarily with a human focus, at least initially, and to use that information for prioritizing chemicals initially. We also are working on adding in exposure predictions so that we can combine that with the hazard predictions and develop higher throughput risk assessments, which is really what the agency is interested in. Just a quick overview of where we are with the program. We've completed screening what we call the phase 1 and phase 2 chemical libraries and released all of the data for those. That's about 1,000 chemicals, with the phase 1 chemicals primarily being pesticide active ingredients, and the phase 2 much more diverse environmental chemicals. Those data have been out for a while now. There's also another 1,000 compounds that were screened in endocrine-related assays only. Those data are also out there. And then through the Tox21 initiative, we have a chemical library that now totals about 2,000 samples, and that's an ongoing screening process. I think there's about 150 assay endpoints that have been screened through Tox21, and most of those have been released, and many of them are in PubChem. And now we're in what we sometimes call phase 3, but this is about another almost 1,000 chemicals that are going through a subset of the ToxCast assays. So we picked a set of the most informative assays with about 300 endpoints, and that screening work is ongoing. We've completed a few of those screening sets, and those data will be coming out in the next year or 2. This cartoon, you all know what high-throughput screening is. It's really just to emphasize that the great majority of the work that we're doing is screening chemicals in biochemical, cell-based, or model organism assays in concentration response format. So we generated an enormous amount of concentration response curves, and that turns out to be one of the bigger challenges that we've faced with the program. The assays come from mostly small companies that work to support the drug discovery industry. It's a very diverse set of assay providers, some in-house, but mostly done through external contracts. They cover a whole variety of biological responses, from cell proliferation to enzyme inhibition, receptor binding, transactivation assays, steroidogenesis. They target most of the major protein superfamilies, kinases, phosphatases, nuclear receptors, GPCRs. The assay designs are very diverse, lots of different types of reporter assays, fluorescent-based assays. And we screen these in biochemical format, against cell lines, against primary cells, even some model organism assays. Mostly human, although some other species are mixed in there. And a whole variety of assay detection technologies. So that creates a significant data analysis challenge. And this lists some of the major issues we've had to deal with. The data are very heterogeneous, coming from all of these different vendors and all of these different formats. The experimental designs are heterogeneous. We don't have full control over how the experiments are set up, because all of this is done through some very defined contract mechanisms. The stability of activity calls over time. So as time goes by, we learn more and more about these assays, and we adjust what we consider an active chemical call. We are always working on developing better methods of identifying systematic false positives as well as false negatives. We have to think a lot about how we present all of these complex and detailed results in a way that the community can make use of them. We have to think about how we communicate those results. And there's also an effort within the center in trying to develop the skills within the community, trying to help them better understand our data and to think about ways that they might do their own analysis of the data. What we've evolved to for the data analysis is this pipeline. We're on version 2 of the pipeline right now. Initially, we received data sets from each of our assay providers in a heterogeneous format, and we used R scripts to convert that heterogeneous data into something more uniform. And then we process it through a series of levels that eventually result in what we call a level 6 data file. And I'll show you on the next slide what that corresponds to. And that goes into the ToxCast database. And then we can export flat files that show our summarized analysis of results. Version 2, we now take our input files from each of the vendors in as much of a uniform, homogeneous format as we can, and they go directly into our in vitro DB. And we have an R pipeline script that converts everything to a homogeneous format within the database, processes it through each of the levels, and then we can put out the flat files of results at the end. So these are the different levels. We start off at level 0 with the raw files that are vendor specific. And then we do a series of data normalizations, defining replicates, concentration indices, assay component specific value corrections, assay endpoint specific normalization. Then we do the model fitting, model selection and hit calling. And then the latest thing we've added to the pipeline is flagging for potential assay interference for false positives and false negatives. The raw data file remains unaltered, and that's always available. All the assays and technologies use the same code, and there's some parameters in there that can be changed for assay-specific platform. We use a combination of statistics to make active calls, so the median absolute deviation, the AIC are important statistics for the pipeline. And then we also will implement a biological efficacy cutoff where we know something about what biological significance might be for a particular assay. We calculate points of departure, AC10s, AC50s. We developed a system of caution flags, as I mentioned, and these are 3 different types. We have chemical-specific flags, which correspond to the analytical QC work that's been done on each of the chemical samples. We have an assay chemical-specific flag, which tries to point out where there's potential for false positives and false negatives, and there's a whole series of those now. And then there's also an emphasis on understanding broad cytotoxicity. We do a lot of cytotoxicity testing on a lot of different cell lines, and we developed some ways to quantitate that and make that information available to be considered while you look at individual assay results. And we're trying to do a better job of helping people understand how to use these flags. This is just a quick summary of our curve fitting protocol. So we try and fit all of our concentration response data to 3 models: a constant model, a Hill model, and a gain loss model. So this third one, this gain loss model, is a very common type of response curve that we see in cell-based assays, where at high concentrations you see cytotoxicity and you see a loss of signal, and that can create a lot of problems for doing good curve fits. So we have this gain-loss model which works really nicely, and we can calculate the AC50 both for the increase in the curve and the decrease in the curve if we're interested in both of those. And then we use the AIC statistic to determine which is the winner of those models. I'm not going to go into the details of this, but this summarizes what was in the in vitro DB recently in terms of the types of responses that we're using to make hit calls, the number of actives, the number of actives in different curve classes, and things like that. But these summary tables are easily extractable from the database. I'm just going to give you a broad overview of the phase 1 and phase 2 ToxCast results. So this is a heat map showing the columns are chemicals, the rows are assays. There's about 800 endpoints there, and close to 1,000 chemicals. And what you can see at the high level here is that there are chemicals that are very promiscuous and are active in a lot of the assays, and you have chemicals with very little bioactivity. And then we have some assays that are not detecting activity in the majority of the chemicals. So those are assays that would be candidates for us not continuing to use because they're not providing us much information. This is a table from a paper summarizing biochemical assay results looking at the most promiscuous chemicals. And I put this on here to point out that the types of chemicals we're dealing with can be considered problematic in vitro approaches. So the number one most promiscuous chemical is phenylmercuric acetate. Whether this is through assay interference or specific biological effects, it's hard to know. Mancozeb is a pesticide that has some ability to react with thiols, and again, this may be kind of artifactually promiscuous. But there's lots of other chemicals in here, so these tributyltins are really interesting compounds. They're very promiscuous, but they have some very potent and interesting effects, especially on nuclear receptors. And then we have these pharmaceuticals. These are mostly failed drugs that are pretty much as promiscuous as some of these organometallics. There's an example here of a detergent-like compound that's very promiscuous but not very potent. And that's probably a good example of really a nuisance or interference compound. And a lot of those are not really relevant biological activity. So what did we learn at the high level? One of the things we learned is that a lot of environmental chemicals are not very selective. They become very promiscuous once the concentration gets to a high enough level. And so this is a cumulative fraction plot of fraction of chemicals which are active in any number of assays. So once you get up to about 20% of the chemicals, most of them are activating 10 or more assays. So they're not very selective. And then the chart so 80% of the chemicals activate 10 or more of the assays. The chart on the right shows the potency for activating the most potent endpoint for a chemical versus the potency for activating 10% of the endpoints for that chemical. And again, about 80% of the chemicals have less than a threefold ratio, so most of the chemicals are not very selective. And we somewhat arbitrarily define that top 80% as being a non-selective response and the lowest 20% as being selective effects. And for the selective chemicals, we put those into an analysis that revolves around an AOP type of approach, where we focus in on those selective endpoints. And the example that I'll give is with the estrogen receptor model that we've spent a lot of time working on in support of the EPA's endocrine disruptor screening program. We, more or less by chance, have a lot of estrogen receptor-related assays within the ToxCast program. So we've taken all the data from those assays. Richard Judson led an effort to build a mathematical model that incorporates the activity from each of those assays and looks for assay-specific interference, assay platform-specific interference, and comes up with a score for a chemical working as either an agonist or an antagonist for the estrogen receptor. And this is not a AOP. Most of these assays are focused on what would be the molecular initiating event or activation of the estrogen receptor, with the exception of the last assay, which is more a key event or maybe even an adverse outcome, but it's a proliferation, estrogen-dependent proliferation assay. So using this assay, well, why we need to use this model is the way that our screens are run. No single screen is perfect and gives us true answer. So this is a set of chemicals run through all of the estrogen-related assays, and they're hierarchically clustered. So the chemicals at the top were active in most of the estrogen receptor assays, and these assays include both agonist and antagonist. You wouldn't necessarily expect there to be a solid red line all the way across. But then down below, you see there are areas where chemicals are active in just one or just a few of the assays. And the assays cluster by the assay platform, suggesting that these interference you see down here drives the assay-specific interference drives the clustering. And the reason we have this issue primarily is because the chemical library that we're screening is really not drug-like. We have all kinds of nasty chemicals in there: solvents, surfactants, compounds that are, pesticides that are made to be cytotoxic, metals and organics, and these things interfere with assays in lots of different ways. So it's important that we figure out a way to deal with that sort of interference. And this model does a good job of that. Here's some examples of that. So on the left are the concentration response curves for the ER assays. The top is bisphenol A, and on the right is the mathematical model derivation of concentration response curve for the agonist, which is shown in blue, and it gives a score of 0.39, which is a high score for an ER agonist that goes on a scale from 0 to 1. The second one is hydroxytamoxifen, so here are the concentration response curves, and in this case, the model for the antagonist gives a score of 0.72, so that's a very strong score as an ER antagonist. And on the bottom is alpha-cyclodextrin, showing a response in three assays. They're all black, which means they're all from the radioligand binding assay platform. Alpha-cyclodextrin was active just in the binding assays, and it produces a score just for interference for that platform, a score of 0 as an ER agonist and antagonist. And alpha-cyclodextrin is known to be able to bind steroid-like compounds, so what it's probably doing is removing the radioligand, the steroid radioligand from the binding assay and artifactually interfering with that assay. And so then we've looked at a series of reference compounds to see how well the model does. The green are positives as a reference compound, the red are negative. And so it does a pretty good job. It misses a couple of compounds classified as very weak estrogens. We have a limited upper testing concentration in the ToxCast program. And so for weak, not very potent compounds, it's not a surprise that we miss those sometimes. On the bottom is a score for the antagonists. All 4 antagonists were strongly positive. Most of the negatives were negative. There's some that had a significant antagonist score, but those are compounds which probably have some selective estrogen receptor activity, which causes them to get, it can be classified both as an agonist and an antagonist. And then the ability to classify compounds from inactive to strong is shown on the right. So each of the reference compounds is in one of these classes, and this shows the agonist score on the y-axis. So it did a pretty good job of estimating the potency of the compounds as well. And then this is some recent analysis of eutrophic compounds that we tested in the ER model, and had also been tested in the eutrophic model. And the blue ones were active and uterotrophic, and again, here's the ER agonist score on the y-axis, and it did a really good job of predicting the effects of most of those uterotrophic active chemicals, and most of the negatives were below our significance cutoff for the model. So based on that, the endocrine disruptor screening program at EPA has published a notice in the Federal Register of the federal government saying that there is an intent to use these high-throughput assays and computational models as an alternative for some of the current assays in the endocrine disruptor program tier 1 batteries. So this is specifically the estrogen, right now, the estrogen receptor transactivation, binding, and uterotrophic assays. And we're now putting a lot of effort into doing the same thing for the androgen receptor and the thyroid receptor to try and replace as many of these more expensive in vivo assays that are part of the EDSP. So I'm going to skip through this pretty quick because I'm going to be running out of time here, but I just wanted to emphasize that we also have a major effort in trying to incorporate exposure science into our program so that we can do risk assessments. And one of the pieces of that is first doing reverse toxicokinetics, which is, we've developed a very simple 2-parameter PK model that measures binding of compound to human or rat hepatocytes and to human plasma, and then doing some modeling to estimate the oral dose it would require to achieve a concentration that would activate one of our in vitro assays. And this is a summary plot of that. So each of these, the bars here, is the range of AC50 values from our in vitro assays converted to an oral dose required to achieve that. And that's in log of mg per kg per day. And then where we had exposure measurements, these are the green dots down here from the Antagonist study, we plotted those. And then what we would look for is where there's an overlap between in vitro activity and exposure estimates, exposure measurements in this case. And those would be chemicals that we would put as high priority for follow-up. But we don't have exposure measurements for organic chemicals, so we've developed the ExpoCast program to predict exposure. This is a very early program, but it's come a long way. This shows the model prediction for almost 8,000 compounds, and some upper 95th percentile and the median exposure values. And then what we are doing is putting now together the range of distribution of the AC50s from the in vivo ToxCast converted using reverse toxicokinetics to an oral dose with the potential exposure from ExpoCast to build this higher throughput risk assessment and find the high risk chemicals where those distributions overlap. And this is a summary of looking at the latest ExpoCast exposure predictions with the oral equivalent factors for the ToxCast assay, the ToxCast chemicals. And then last slide, we've had a major emphasis right from the beginning to try and make all of our data available. It's been a challenge, as I mentioned in the first slide, for a number of reasons. The latest version of how we're doing this is through what we call the ICSS ToxCast dashboard. So this is available through this web link. There'll be a new version of all of these data out in the next week or two, but you can access it right now. You can browse the data, various visualizations, and you can download single chemical data or data sets. And then you can go to our website and download the entire, all the flat files for all of our assay platforms. And you could even get the entire in vitro DB if there was real need for that. And with that, this is the nice calm lake at the EPA that hopefully won't be flooded after the hurricane. And this is the top tox group as of last year. So, thank you.